Hi guys, in this video we're going to talk about displacement versus distance traveled. So let's imagine we've got a person walking 50 meters one direction, they turn around and come back to their same starting point. And here's a bit of a diagram. They've walked 50 meters one way, they've stopped, they've turned around and they've come straight back to their start point. Now in this situation we can all agree that the distance traveled is just going to be 100 meters, so 50 plus 50. However, the displacement is 0 meters. The displacement is how far an object is positioned from its original start point. Whereas distance traveled is the total distance that an object has actually moved since leaving its original start position. So graphically on a velocity time graph, the displacement is what we call the signed area. What I mean by the signed area is, so if I wanted to find the displacement of this object, which is the distance from its start point after 15 seconds, I just have to integrate this velocity function between 0 and 15. Now on the same velocity time graph, the distance traveled is what we call the exact area. So the exact area is finding the area underneath the x-axis and adding it to the area above the x-axis. So because the area underneath the x-axis is a negative, we've got to use a negative sign in front of the integral to change the value back to a positive. Then once we've done that, we can just add both regions, and that will give us the total distance traveled. So this here is a graphical example of the first situation that we were talking about in this video. So if someone walked one direction, they turned around and walked in the other direction. And in this situation, we're saying they're walking at a speed of 20 meters per second. So probably not realistic as a walking speed, but that's all good. So in this situation, right, the displacement, we know the displacement is going to be 0, right? Because they've ended up at the same start point. The area above the x-axis is the same as the area below the x-axis. But if we go and do that algebraically, so we find the integral, we add them together, we end up getting 0, as we would expect. Now, if I wanted to find the distance traveled instead, then I've got to put this negative sign in front of the second integral, because the second integral, the area between the curve and the x-axis is underneath the x-axis. So for that reason, I've got that negative there. Some textbooks will use an absolute value sign as well. An absolute value sign just removes the negative sign from a number. Either way, completely fine. So when we go and crunch the numbers for this, as we would expect, I'm not going to go through the algebra, that's assumed knowledge, but as we would expect, we get a distance traveled of 160 meters. So just some other useful notes. So to calculate the distance traveled, you often need to find x-intercepts first. The reason for that is because it just helps to identify what regions are above the x-axis and what regions are below the x-axis, which is needed when you're integrating. Something else that's really important is that whenever you are integrating from acceleration to velocity, or if you're integrating from velocity to displacement, read the question really carefully, because sometimes it will give you initial conditions which will help you to be able to solve for C after integrating. So a classic example is if a question says an object starts from rest, that means that when time is 0, the velocity is going to be 0 if an object is starting from rest. One last thing too that is noteworthy. So velocity functions can vary in complexity. So in this video and my last video, I've kept it quite simple, but velocity functions don't just have to be linear lines. They can be parabolic, they can be cubic, they can be essentially whatever is suitable to the context. But no matter how complicated a velocity time graph is, the same basic principles in this video do apply. For example, it's as simple as the area under the curve is the displacement and the gradient is the acceleration. In the next video, I'll be going through a couple of worked examples of some complex familiar and complex unfamiliar questions related to velocity time graphs.